All right, in Unit 11, we're starting to look at these logarithmic functions. So logarithmic functions are going to be the inverse function of an exponential So it's the inverse of the exponential function, and really a logarithm for all the things we'll talk about logs, a log is really just an exponent. So a log is just the exponent of an exponential. So if we think of an exponential function, we typically think of it as y equals b to the x. So this is our classic exponential form where we have a base raised to the x power. So one of the most important things you can commit to memory is when you switch to log form, you can freely switch an exponential to a log form because a log form is just a different way to write the exponential form. And the key is we want to get this exponent by itself because a log is just this exponent. So this exponent can be written by itself, and we would just change this exponential to a log function. So we say log base b of y. So it's really just a rearrangement. So you'll see this b becomes the base of the log, y becomes the input, and then x becomes the value by itself. So you could switch back and forth of these freely. So you can use this idea to graph, to solve equations. This little relationship right here is really how you can do most of the things in this unit. So just a quick example. Let's just do a quick example, see how this works. So if I do 2 to the third, we know that's 8. So if I put it into log form, it's saying 3 equals log base 2 of 8. So I'm claiming if you put log base 2 of 8 into a calculator, you will get the number 3. Now it's kind of tricky if you're using a general handheld calculator. The way we type this in is we do log of 8 divided by log of 2, 8 being the value and 2 is the base. So if you put log 8 divided by log 2 in your calculator, you should get 3. So it's a different way to write it. Now obviously doing something like this doesn't have much merit because we already know 2 to the third equals 8. But if we didn't know what that exponent was, it could be helpful for us. So the first thing I'm going to do is I'm going to look at how to graph one of these. So if I look at this function, I have f of x equal -4. I did log base 2 of x minus 2. So my base function is going to be f of x equal to just log base 2 of x. Now, a couple things about this function. We know all logs have a vertical asymptote, and it generally starts at 0 unless you start moving it left and right, which we will in this case, but we'll start with this. And then there are 3 points that we can always find. So those points, if you think about these 3 key points, they are the base comma 1, they are 1, 0, and 1 over the base -1. So our base in this case is 2. So I know the points I have in here are 2, 1, because that's the base and 1. I always have 1, 0, and then 1 over 2 and -1. So those are my 3 key points for my log base 2 of x. So I want to start with these. So these are my starting points. Now obviously I have some transformations here you can see. So when I'm graphing this one, if I look at the transformations, here this is a shift to the right of 2. And this is a vertical stretch and a reflection by -4. It's a vertical stretch of 4 and then a reflection of the negative. So really you're multiplying all the y's by -4. So the x's are going to get added by 2 and the y's are going to get multiplied by -4. So So that's how we'll get our points for our graph. Now, one thing we have to really be careful of is when we move all the x's to the right, that includes this vertical asymptote. So my new vertical asymptote is going to be at x equals 2, because if I add 2 to 0, I get 2. So there's my vertical asymptote. Now, if I do my new points just by adding 2 and things like that from my key points, adding 2, I'll get 4, 3, and 2.5. And if I multiply the y's by -4, I'll get -4, I get 0, and I'll get +4. So if I plot these points, 4, -4, looks like it's about there. 3, 0 is there, and 2.5 +4 is here. So it's going to look something like this. And it continues on and on and on. So I can see the domain is generally always going to be from that vertical asymptote to infinity. Now, generally, I would tell you, generally logs kind of look something like this, where they grow really slowly. The reason this one is upside down, remember, is because we reflected it. We flipped it over the axis. So I just wanted to point that out. But that is an idea of what our graph would look like. And the key things here, remember, you have these key points for every graph, and then just make sure that your asymptote gets moved left and right. It's always 0 unless you shift it left and right, and then it will change accordingly. So last kind of thing we see in this section is one thing that we'll talk about more in the next section as well, is solving exponential and logarithmic equations. Now, quite honestly, all these can be done with that one relation I told you earlier. Y equals b to the x is an equivalent statement to x equals log base b of y. So for the first one, I have something that's written in log form. I'm going to try to switch it to exponential. So this says log base 3 of x plus 2 equal 4. Now if we do this right, magically our variable should be by itself, which in this case it becomes, because it'll say whatever was the base is 3, to whatever power is x. Well, x over here is what's by itself, so that is 4. So this becomes 3 to the 4 equals x plus 2. So remember, switching to log is just a rearrangement of the terms. 3 to the 4th is 81 equals x plus 2. And then I'll simply subtract 2, which gives me 79. All right, the second one has this e, and if you remember doing your notes for Unit 11 on the Ed puzzle, they talked about the difference between common logs and natural logs. Natural logs have this e. So when I switch this one's in exponential form. I'm going to switch it to log. So the exponent goes by itself, so that's -3x, and it's log, but the base is e. So when we have a base e, we just write it as ln. You don't have to write the number, you don't have to write the subscript. When you see an ln, that means it has a base of e. So -3 equals ln 7. If you want to write a little e down here to make yourself feel better and keep your place, that's fine. But generally we don't. We just write it like this. And again, that's just because what was x, what was the exponent, it goes now by itself. The base goes down here in the log, but it's kind of invisible because it's e, and then whatever was by itself goes in there. So you can see I'm just matching these up. So then I can divide both sides by -3, so my exact answer is ln of 7 divided by -3. And you're certainly welcome to put this in a calculator and get a decimal approximation, but that is our exact answer. All right, finally, we have log of y, 216 equals 3. So this is in log. I'll switch to exponential. So we'll have y to the third, because it's the base to the exponent. Remember, in a log, the exponent's by itself, equals 216. So now we have to solve this. We have to take one extra step. To get rid of the cube, we'll take a cube root. So what number times itself 3 times is 216? This is a nice one. It is 6. 6 times 6 times 6 is 216. So this is all about just doing that rearrangement, just kind of doing it over and over again, just trying to get them to match up where they're supposed to be. So those are just a couple examples for your worksheet of the day on Unit 11. Obviously, if you have questions, concerns, please reach out. I'd be happy to meet with you and help you out.